Okay, I think we're good to go. Would you keep an eye on the chat, make sure people can hear me there? And I'm going to try to stand as still as I possibly can. So welcome to the DLS for Thursday, September 22nd. Today's speaker needs absolutely no introduction. I've known him, it feels like all my life. Great guy, wonderful to work with, really, really cool. So relaxed and wonderful at speaking in front of groups. It really is a pleasure to be able to introduce him. Okay, thank you. Okay, so thank you for that kind introduction. Well, we don't really need an introduction, especially because I gave a little vignette a couple weeks ago. So you've got some of the background information on me. I want to give a little introduction to the talk. I was looking back through my slides and looking back through my history, and I haven't presented to the department since I first interviewed here in 2011. One of the things that we try to do as faculty is, well, we have a mandatory review every 5 years. And one of the things that we try to do is give presentations so that everyone in the department can see what we're up to and so that we're still contributing members of society. So thinking about what I wanted to talk about, it's been over 10 years, that's a long time. And thinking about what I do, I'm a Earth system scientist or a critical zone scientist. And this is how I view the world. I view the world this as a figure from a paper that I was able to do with John Chorver and a number of colleagues, diagramming the critical zone. And it's an open system thermodynamic environment where rock, water, life all interact with climate and feedback to control climate. And that's what really excites me. It's so fun. I have the Sudoku puzzles over there because we work at many different scales and many different disciplines. And you can think of a relatively small, well-defined project up there in the top left of the Sudoku. And it's pretty constrained, pretty much under control. You can feel good about what you're doing. As we go to larger spatial, longer temporal scales, we bring in more disciplines, the Sudoku puzzle gets more and more complicated. And so that makes it harder to unequivocally understand what is driving responses or phenomena that we see. But at the same time, it also gives us insight from many, many different disciplines and approaches and techniques. So we can bring in biology and geochemistry and hydrology, isotopic tracers, climate dynamics, boundary layer meteorology. We get lots of little windows to figure out what the number can't be in the Sudoku square. And when I do Sudoku, I do it in pencil. Because what we're doing is like, I think this is what it is, but it's a tentative conclusion, right? And then you bring in other information. So that's the overall rationale of what we do in our group. There's no way that I can talk about all the cool things that we do, whether it's acid mine drainage or carbon sequestration, landscape evolution, soil development, beaver dam analogs, all sorts of fun things that we can do, we can bring this framework into. So I'm going to talk about the title of my talk, and that's climate change and water balance in the Western US. And more specifically, the older I get, the more I want to make sure that I move the research that I do and my group does from the broader scale conceptual and theoretical framework and understanding to actually putting it to work. How do we reach outside the communities, the people that use this information? And so these two figures here, I love snow hydrology. This is a figure that's meant to represent basic research, the fundamental understanding of grain scale, mass and energy balance within the snowpack. So cool. Kind of hard to relate to everyday life and decision-making, which might influence something like the reservoirs in the Colorado River. So how do we bridge that gap? The first thing that I need to do, or I guess this would be the third thing, because I introduced my background in the topic. So the third thing that I need to do, and the most important one, is that this is all work from an amazing number of really great people. My students and postdocs have done all this. I get to go along for the ride and hopefully nudge them in the right direction now and then. That future generation is really absolutely amazing. Most of these are my students or postdoc mentees. A handful of them are loaner students or loaner postdocs. We have a great group of collaborators across the Western, actually across the world now, where they'll go, their advisor, their primary advisor may go, oh, you got great skills and it's kind of crazy ideas. I know this Paul guy, it's Paul Brooks guy. He's got crazy ideas too. Why don't you talk and see if you do one of the chapters of your dissertation with them? And I'm going to try to call out a few of these folks as we go through and I show you results. The rest of the talk is going to be a very broad brush approach. We're not going to go into detail. If you want hard scale detail, you're not. It's going to be a snapshot of here's a greatest hit, here's a finding, and here's how we think it's useful. I don't think we need to entertain anyone who lives in the Western US is aware that we've got problems in terms of water resources. We've designed our infrastructure, our legal and physical infrastructure on conditions that don't exist anymore, if they ever existed anymore, when you think about what we do for the Colorado River. We've reached the first tier 2 shortage on the Colorado River. We've seen record low reservoir levels throughout the state of Utah. This is a widespread phenomenon. And so just as a quick primer, a quick background on where our water comes from in the West, it comes from, I'm not supposed to walk away, it comes from these green higher elevation areas, relatively small environments. It primarily falls of snow and it recharges groundwater and it runs off into the streams each year. This western half, western 2/3 of the United States is dominated by this, but it's an analog for what's happening in some of the most stressed places around the world. The Middle East, China especially, very powerful, sometimes in some ways unstable. They all share similar environments in large areas where they depend on snowmelt-derived water resources. And the challenge that we've all seen and hear about endlessly is the directional climate change and wide-scale warming, especially since 1980. Our mountain environments are warming faster than the globe as a whole. And we're seeing declines in streamflow. This is the Colorado River on the right. And this is well documented. We see and we read about it all the time. But I would argue that as hydrologists, I'm part of the hydrology community. It's probably the hat that I wear most often now. We haven't done as great a job as we could in bridging new information and new knowledge and putting it into tools or guidance that managers can use, the people that are actually charged with that. This is an example of what's going on. Our focus, widespread declines in snowpack. This is Phil Mote in 2005 published this first paper, and he followed it up in 2018, or he and his colleagues followed it up. And you see that there's widespread. The red circles are the decline in April 1 SWE. April 1 SWE, it looks pretty bad, and it is pretty bad. But we need to stop and take a minute about April 1 SWE. April 1 SWE is not an objective metric. It's a compromise based on when people were primarily collecting measurements by hand, traveling out in the field. When could they get to the field? When could they get information? The figure on the right shows the snow-free day, and this just came out actually on Monday in P+E+T+AS, shows how the snow-free date varies from March 1st to June 1st. You can subtract about a month or 6 weeks from that, and that's the variability that we have in the day that peak SWE occurs. So things are definitely changing, but if you look here, you might think that we have 80% less snow. A few places we have a little bit more. The timing is changing tremendously, and it's not uniformly distributed across elevations or geographies. So we need to come up with better guidance. We do know that overall, these changes in the timing, the amount and the timing of snowfall are having huge impacts on streamflow. This is a figure that Meg Wolf put together. On the left, we're showing 2021 water year, April 1st SWE. Again, this convention of when we assess SWE, slightly below average, 70. West-wide, I think we average somewhere around 91% or so. So not a horrible year in terms of snow, a little bit below average, but streamflow was horrendous. All the dry reservoirs and the photos that I showed on some of the previous figure, many of those were taken last year when water managers expected that runoff would reflect the amount of snow on April 1st. And the runoff efficiency, the streamflow was really low. And those of us who focus on hydrology know that part of this is due to climate change, and part of it is natural. There's tremendous variability in runoff efficiency. One of the great things we know about Utah, is we have tremendously long records of streamflow, better than anywhere in the country, and pretty much better than most places in the world in terms of the number and diversity of stream gauges we have that go back over 100 years. And when we look at streamflow, we can plot on the x-axis here, deviation of mean annual precipitation over that 100-year record. It's like, all right, average precipitation can result in 50% above average stream flow or 50% below average stream flow. That is a water manager's nightmare. And it's only being exacerbated by climate change. So we wanted to address that. And many other people do. And there are three broad approaches. Many people are trying to work on this. We're just one group of it. There are three broad areas. People that are looking for more data. So we have remote sensing. We have all sorts of data assimilation programs. How can we mine data archives? How can we bring more data to bear, especially on spatial snow cover? Our remote sensing capabilities have advanced tremendously. One is more powerful models. The National Water Model is a huge national effort to add physical realism into model predictions of stream flow. And then the last area is improvements in model structure. And that's the area that we work on. What are simple things that we can do that are not captured in the conceptual models that our current predictive models are based on? What are those little pieces of new knowledge that we can transport relatively quickly? I want to give you a background on where we are right now. The most widely used models for stream flow prediction in the US are very similar, are either the Sacramento model, which is used by the Colorado River Basin Forecast Office, Sacramento SMA, soil moisture accounting, or Snow 17. These models are both 50 years old. They're incredibly powerful. They're incredibly useful. They're well calibrated. The individuals that use them have heuristics and experience to help guide prediction, but they still miss sometimes, like we did in 2021, in terms of filling the reservoirs with an average sweet year and very poor runoff. So George Box famously said all models are wrong and some are useful. These are incredibly useful models, but they still don't get everything correct. The simplification in Sacramento SMA is it really heavily focuses on vadose hydrology. I see some folks from my hydrology class in the room. Hopefully some more online. That's what we've been studying this week. Focuses heavily on that and it doesn't look at the big picture. Snow 17 simplifies everything that happens to a snowpack, to a temperature and a coefficient. And those scatter plots there are how variable that coefficient is, melt related to change in temperature. Not really a great predictor, it varies all over the place. So powerful, but we can do better. The way that we do better and the way that we've been trying to do better is sort of invert our standard water balance model. A typical water balance model, a typical approach starts with forcing the system with a certain amount of precipitation, then using whatever the temperature is to evaluate and predict what's going to happen to Q, stream flow, E evaporation, T transpiration, which are usually grouped together, and then delta S or change in storage. So we now are way better at identifying change in storage with all sorts of different metrics and approaches than we were 50 years ago, even than we were 10 years ago. And it's been widely recognized that ultimately in the near land surface, hydrology is a competition between the amount of precipitation that goes back to the sky and the amount that can eventually make it to stream flow or recharge groundwater. Binary decision, incredibly complicated, and it's mediated by storage. 1933, Hortonian overland flow. Again, back to vadose hydrology class. Penman asked, what happens to the rain? Most of the hydrology work was focused on runoff in his time. And he's like, wait a second, most of the water is evapotranspired back to the sky. And it's mediated by what's in storage. And then those of you who think in broad scale energy, water relationships, the Budiko or the Lvovich framework, it relates energy and water availability. Again, there's been tremendous work over the last 50 or 60 years that tries to understand, my mouse isn't working and I'm not supposed to walk, The shape of that curve, the small shapes of those, the variability in the shapes of those curves mean a lot for water availability to plants or for people that live downstream. And they're mediated by different ways that we represent storage. Storage clearly is what controls that partitioning, but it's largely excluded from the Sacramento model and the Snow model. They're simplified representations. So we're going to run off the premise that almost all precipitation enters soil. We'll show you some data to support that. And then where is it and how much of it is available? Pretty simple premise. I like simple ideas that we can compare things to, compare data to first principles. And here's one of the examples where I got to borrow a student from someone else. So during sabbatical, travel was somewhat limited. So I chatted with some of my friends and former postdoctoral mentees. And one of them had, B. Gordon, was just finishing up her PhD and she wanted to do a nice summary. Why is snowmelt variability, snowmelt runoff variability so variable throughout the West? Why does a model for one place not work for another place? What are the underlying causes? Absolutely amazing. It was a fantastic way to spend some of my sabbatical time. Brilliant, brilliant. She's now a postdoc at Stanford and just, I can say kicking butt. That's not bad. She's just kicking butt. All right. And so in our framework, in B's framework, so which we all contributed to, we're really talking about two types of storage, snow storage. So a la Snow 17, the simplifications there. And we're talking about soil and groundwater storage. So how much snow is there? It's a function of how much snow falls. And then the amount of snow that's lost during the course of the winter, which we don't consider and Snow 17 doesn't consider. How fast it melts. That's a function of how long it's exposed to the atmosphere. That melting snow can evaporate during the season. The longer it takes to melt, the more likely it is to evaporate. The faster it melts, the more likely it is to recharge. And then where is it actually stored? So those are the things that we've been trying to address a little bit. I want to run you through, again, a number of vignettes. Compare the Snow 17 model, tremendously useful when you don't have a lot of information. You can't run a snow energy balance model. On the right, if students, anyone, I don't think anyone here has taken my Snow Hydrology class. It's been a few years since I taught it. But this is an empirical representation of the mass and energy balance equations of the snowpack. These are one step away from the physics, but this is what you need to know to understand what's happening in a snowpack. We can't put that in an operational model. We don't have the data, well, we can, but we don't have the data or information to objectively evaluate it. So, and none of them deal with those vapor losses from the top of the snowpack. So this is a knowledge gap that we've tried to address and we've been focused on for a while. And again, by we, I mean my students and postdocs. They did all the work. Here's an example. And so this came out a year after my last seminar to geology and geophysics, right? So I'm going longer than my 5 years, but things that probably haven't seen before. This was a Snow Hydrology class project. I like to involve my students in advanced classes to actually, if you're going to do a class project, let's do something meaningful and publish it. This is a particular example where it shows widespread warming, no big shakes there. But other than that, not really, when you actually look at the day that P Q+E occurs, not tremendous changes. The biggest thing that we see is overall slower melt and hints of changes in the day of P Q+E, small changes in the day of P Q+E, and hints of SWE loss during the winter. SWE is snow water equivalent, so the total amount of water stored in the snowpack. Heavily jargon as I present to a diverse group. You guys can call me out on it. Anytime you can call me out on it. And so these are the two things that we saw. The figure on the left is ablation rate, winter, so loss of snow from the snowpack. The bars give the rate of change. The reddish brown ones are ones that are significant. What you'll notice is most of them fall with greater ablation rates. And so that top figure shows what ablation rates look like. So early in the record is the 1980s. Late in the record is 2015, 2016, somewhere around there. That's widespread throughout the West. We're losing more snow. And these are all data from very, very protected sites, extremely protected sites, snow-tell sites, if you're familiar with those. The other thing that we see is we see earlier melt and slower melt. So neither one of those things are good for water resources. They're reducing the amount of water that we potentially have. And so that's getting a little bit closer to thinking about what the threats might be and how it could be useful. But we wanted to make something that was useful for water managers in their own unique locations. And the way they could determine whether or not their snowpacks were at risk. You see lots of articles that say at the end of snow, there'll be no more snow, tremendous changes. And some places may experience that, but others won't. And it shows that the largest control on that variability on what happens, does it melt earlier or do we lose more of it in the winter, is the humidity of the environment. And that's because the latent exchange between the snowpack and the air is much larger than the sensible heat exchange. Everything else is roughly held constant because the solar angle, which is the largest energy input, varies the same year to year. If we have large variability in solar input, we've got way bigger problems than this, right? And so this is a snow hydraulic in 2019, right before COVID. We have a bit shorter snow-covered season. It's largely happening earlier in the season, and that's what this was about. The students were interested in what does that mean for the ski area industry? Imagine that, we're in Utah and students are interested in the ski industry. Oh, come on, help me out here. Thank you, I appreciate that. Okay. And so what we saw in the class was that widespread warming and something really surprising, earlier first snowfall. The first snowfall comes earlier in the year. If you stop and think about it, climate change puts more water vapor in the atmosphere, mountains call uplift, we should see more snowfall. Not that surprising if you stop and think about it. But how do we square that with the fact that snow cover season is getting shorter? And that is also with those increasing snowstorms, we also have increasing rainstorms and a larger fraction of rain in between. And that results in increases in early season melt. So during the shoulder seasons, it's harder to start a snowpack. I tell my snow hydrology class, the two hardest things to do in the world in snow hydrology is start the snowpack. The second hardest thing is to get rid of the snowpack. The energy balance feedbacks make it hard to start and hard to get rid of. Okay. Man, this is quite the whirlwind. I realize we still got a lot to cover. So those are large scale processes and there's predictions. We could say, are you in a humid climate, a cloudy climate? What are your local risks based on your region? So that's helpful. We've given that to folks. People are starting to use it in Arizona, New Mexico, California. I'm going to Wyoming this weekend and early next week. We're going to see if they start thinking about this approach, and we use it here in Utah. So it's starting to make inroads to look at your geographic location. But mountains are incredibly heterogeneous environments. We know that. Anyone who goes skiing knows where the best powder stashes are going to be in those protected environments when you go backcountry skiing. We know that there's a lot of heterogeneity in there. It's associated with elevation aspect. I love this photo. I've been using this photo. This photo was probably in my talk in 2011. It shows the heterogeneity of vegetation associated with aspect. Nothing grown on those south-facing sides and variable forest on the north-facing sides of it. But those forests are changing rapidly between fires, drought mortality, insect mortality. The characteristic of what we call the boundary layer is changing rapidly. And that boundary layer mediates those regional scale solar radiation, temperature, and humidity effects that we saw because it regulates radiation and it regulates wind. And so now we're changing the boundary conditions. So we have another piece on top of directional climate change that's altering our snow water resources, our snow storage. And so this is a nice cartoon which shows how an individual tree affects solar radiation and wind. On the right side of this tree, on the left side, the right side of the left side of the figure. Okay, so there's a tree on the right side of that tree. That's the north side of the tree. You see that through the course, through February, March, and April, it's accumulating snow. On the south side of the tree, you start losing snow in between February and March, and it's gone by April. Tremendous heterogeneity influence on the energy balance of the snowpack. A brilliant student in 2015 took this and put it in a meter by meter square model. Patrick Broxton et al. He's another one of these borrowed students. Oh, let's go do one of my chapters with Paul. I took my Snow Hydrology class. I've got mad coding skills. I can do this. Put together this fantastic model that solves mass and energy balance on a meter by meter scale in terms of solar radiation, wind, latent and sensible heat fluxes. It's a really cool model. It's wonderful for learning. It's wonderful for querying what's actually happening in the world. All models are wrong. What did we get right? What did we didn't get right? But it's not wonderful for use out in the real world. We can simplify that. We can't give that to a water manager and ask them to totally change how they manage their forests. What we can give them are simple models of energy balance. And on the left, these figures actually should be reversed. What I'm showing on the right are the influence of solar radiation on net snow accumulation, not including the difference between vegetation and snow has very different reflectivity. Looking at just the effect of vegetation on the next figure, figure B, C, looking at the effects of snow, and D, looking at those effects mixed. And you'll see that snow on the hill has a tremendous influence, and it looks much more, the mixed albedo with snow and veg looks much more like the snow. The net effect, the take home from that, is there's a 50% reduction in snow cover in many locations in this catchment, based on its position and how solar radiation is reflected from the snowpack. So that was long coming. Vegetation has a lot of effect both locally and regionally. And we now have the information to actually evaluate that. And what the figure is showing on the left is those are LiDAR-derived snow depth measurements translated into total SWE. We see the arrow points to the north. On the east and north-facing side of the catchment, you have much more SWE than you do on the west-facing side. And on the west-facing side, you see that's where trees really have a huge effect. If you're on the south or west side of the tree, it's a horrible place to be a snow molecule. If you're on the north and east, it looks a lot like if you're on the north or east-facing slope. So the trees are changing that environment, and we can now give water managers maps based on this primary control on solar radiation. Oh, sorry. Now Bailey Olds is working on this here with Salt Lake City Public Utilities, and they're very concerned about management of the forest here along the Wasatch Front, the potential for impacts of fire or whatnot. And so this is a cartoon model of one of her study sites, which diagrams these major fluxes, but then puts it into a readily accessible framework. And we can use that to determine what canopy cover, and more importantly than just the total, canopy cover is the number of trees on the landscape. Is it 100% forest or 0% forest? Somewhere in between. So what canopy cover we should have and what its orientation should be, and where we actually maximize the protective role of veg through shading and minimize other roles through interception. The take home from that is that traditional forest thinning, which is what this picture shows, that's what the Forest Service has been doing for decades for fire and water management. May be good for fire, but it's horrible for water. It exposes the snowpack to sun and wind, and so you actually will get less water with this thinning strategy. If you put them in clumps, you could do much better. And we've seen that. We've looked at many individual sites that show that when trees die, whether it's due to beetle kill or forest fire, what I'm showing here, we go out and we do hand surveys, manual snow surveys, that we don't always get more snow. We lose a lot to the atmosphere, and then we don't get more stream flow. A really nice paper just came out Monday, that P+E+T+AS paper from Stephanie Comp at Colorado State, shows that this is happening throughout the Western US. Really nice piece of work. Okay. I'm gonna take a break. quick break and we're going to shift gears. So now let's look at some of the simplifications in the Sacramento model. And I mentioned earlier that it focuses really on the near surface environment. Those of you in the the hydrology class, we just finished that vadosone section. You know how incredibly important it is, but it's not the whole piece of the puzzle. Laura Condon recently published a paper that asked the question, how deep should we consider the catchment? How much water is potentially contributing to stream flow or contributing to vegetation? This particular model preferentially routes precipitation to surface overland flow in the stream. And there's not a tremendous amount of volume communication with the deeper subsurface. And again, we're taking that equation. I was editing this up until right before I came here. So clearly, you can take the as away. So we're just going to rewrite the basic water balance equation. P equals these things, forcing it with precipitation, and then looking at storage and inferring what happens by changes in storage. Just a slightly different way, like the Sudoku. You're coming at a particular grid cell from a different direction. There's a tremendous amount of information that catchments store much, much more water than we think. I show this to show my students that I actually once did a lot of field work in winter. That's back when I was a graduate student on Niwot Ridge. Dave Bowling knows that site. So we were putting tracers on the snowpack and we recovered the tracers in the soil. We thought we were looking for atmospheric pollution, the fate of atmospheric pollutants. Were they being modified in the snowpack or were they being transported in surface melt into streams and hurting, deleteriously affecting aquatic ecosystems? And it turns out that the water almost all infiltrated in the soil. Maybe not directly. It took some convoluted paths through the snowpack in the soil, but it all was recovered in the soil. Sarah Gotze, who's now up at Idaho State University, was working with Jim Kirchner and did a really nice analysis. That center figure is what's called chemostasis. And the chemostasis has been observed in the vast majority of catchments around the world. And what that means is the chemical constituents of elements derived from mineral weathering from the host rock are very stable, even as discharge increases orders of magnitude. We use small variability in chemical concentrations. We talk about positive or negative hysteresis. We've been doing that for years. And then it's like, Sarah and Jim were like, wait a second, you're missing the big picture. It's hardly changing at all. That line from top left to bottom right in each one of those figures is what it would look like if we were putting in more and more fresh water from snowmelt. And that's obviously not what's going on. Another borrowed student, Marty Frisbee, he was at New Mexico Tech. That sounds, borrowed students, great opportunity to work with another great student. We actually did a reactive modeling. And what we're showing here, or what Marty's showing here, is that the vast majority of water samples show signature of extensive interaction with the soil and subsurface. And most of them are in kinetic equilibrium, only at the very, very top of the catchment. This is a 100-kilometer long catchment. Only at the very, very top do the chemical signatures show signs of being in disequilibrium on what you would expect if the water had just sat there long enough for the reactions to balance each other out. So the evidence for this is tremendously widespread. So that's why we say all water enters soil and why we need to focus on storage. Sally Thompson did a really nice conceptual work of this. It said if all the water enters soil, then the water that's available to vegetation at any point on the landscape is a function both of the precipitation that falls, the subsidy from upslope, and potential losses going out the bottom to subsidize something downslope. Shannon Tai, who was here as a postdoc, and she's now at, Sally's at University of Western Australia. I should tell people where. Marty's at Purdue. Anyway, they're all doing great stuff. Shannon did a really nice set of analyses looking at forest mortality throughout the Western US. Again, with this model that the water available at any location is a function of the local precip and the balance of all this water in the ground, either coming in or moving out. So the water balance model is way more complicated. And this is from Shannon's work, and she shows very, very clearly, this is a widespread aspen mortality. Bill Andreg has worked a bunch on this, a number of folks in Colorado, throughout the West, but especially in Colorado, widespread aspen mortality due to drought. And that mortality is primarily located in areas that are characterized by divergent flow and an absence of subsidy. So more water in the ground is moving away from them than they're getting from an upslope subsidy. So they have a double whammy of low precip and the loss of water that's stored in the subsurface. Where if you're in a favored location, not a problem whatsoever. You have that subsidy.
How do you know about the direction of convergent or divergent flow? Is that just based on digital elevation models? Or?
No, it's a hydrologic model that Shannon put together. It's a relatively simple one. She's done several. One was with ParFlow, which is a well-established groundwater model. Another was a simple model that we could easily port using a topographic index and estimates of hydraulic conductivity. Some of the things that we've done, we've worked on carbon sequestration. First, we got to get carbon into trees, then we got to get it into the soil. So the first step was getting it into trees. And this is Tyson Swetnam, who was here for a while, 5 years ago now. Man, time goes quickly. And so what we're showing here, just very, very briefly, is that the amount of biomass stored in trees in a catchment is higher at lower elevations. And it doesn't matter whether you're at the Como Creek catchment where mean annual temperature is -1, or Batasso Preserve where mean annual temperature is 8 degrees C. We see this reproducible pattern and our LiDAR imagery, and now instead of looking down like we were on snow cover, we're now looking at a cross-sectional view, and you can see much larger trees, much more biomass as you start to work your way down the slope. And this is largely scale invariant. And that's what the figure on the bottom shows. This is the second derivative, the rate of change of slope. And it shows that biomass on the scale of 10 meters, any scale from 10 meters greater, responds to that rate of change of local slope. And that means essentially when you have more standing biomass, the trees are more productive. It's because the slope is going like this. When you have less, it's because the slope is going like that. Convergent versus divergent flow. Okay. So that's quite the whirlwind tour, and we're not done yet. So, but how do we put this into terms of water management? I gave some sort of hints, ideas, what we can do with regional analysis and communicating that to folks. We're communicating the forest management to as many folks as we can. FORFRI is the largest forest management experiment. It's in the 4 forests of Northern Arizona. We're working with partners in the Salt River Project to have this forest management and understanding what's going on in terms of snow and in terms of subsidy there. But can we move a little bit more broadly? And this is going to bring us back to home. And one of the reasons that I'm really excited about being here at the University of Utah, and one of the things that attracted me here years ago, how do we have impacts on this? We're in an absolutely fantastic location to study the climate's effects on snowmelt derived water resources. Our snowmelt derived resources, we can walk out the building and look at them. We can walk out the building and not look up and see exactly where that water is being used. That's not like in the Colorado River, where it comes from Colorado and is used in Los Angeles or Yuma to grow lettuce, or Maricopa County in Arizona to grow some of the best cotton in the world. You know, fill in the blank. It's tremendously distinct source and use there. It doesn't seem real to folks. Here it's present. And we have this tremendous record to have streamflow records. This is a dozen catchments in the Wasatch and the Uinta Mountains, going back over 100 years. Absolutely insane. We don't have that anywhere. That lets us see long-term, not to the scale that we have. There are a few places, Embudo, the Rio Embudo gauge, where you grew up, Dave. Yeah, you're getting referenced a lot here. In New Mexico is has older records than this, but it's on a large river, or what formerly was a large river, the Rio Grande. And so what we've done is we have this signal with directional warming in the top, no real change in precipitation, but tremendously variable stream flow, plus or minus 50% a year based on precip. We wanted to assess storage. We can't drill wells. Even if we drilled wells, what would 1 or 2 wells mean? Incredibly expensive. We used base flow, winter base flow, when all the precipitation that's coming in the catchment is accumulating in the snowpack, and when the trees are probably doing very little, if anything, in terms of transpiring. Relatively stable flow. Now, compared to the peak of snowmelt, base flow looks pretty small. But if you just look there, there's tremendous variability in base flow from year to year. And that's tremendous variability in groundwater storage, is what we're able to plot over 100 years. And it looks like this. When we put those dozen catchments together, they all behave coherently. Clearly, this isn't an artifact. Oh, there's a little bit of ice in the gauge here, or this side is like, they're clearly responding to some sort of forcing that we hadn't recognized before. Groundwater storage, large amounts of groundwater storage responding to a coherent climate forcing. And that metric, groundwater storage, reduces the uncertainty in stream flow that I showed earlier, plus or minus 50%, by half. Just that one metric, that's actionable information that can be used by water managers. It's January. It's pretty cool. And it's based on chemostasis and isotopic tracers and all this cool stuff. How can we come up with an actionable metric? That's our actionable metric. Meg Wolf, that says in review down there, has shown that the proximate drivers of this are 4 years of antecedent climate. And groundwater storage is lower when you have warmer years. Oh, that makes sense. And it's consistent with plants using more water in warmer years. It's higher when you have more precip. Okay, that's kind of a gimme, right? We would expect that that would be the case. But it's also higher when that precip melts faster, when that snowpack is no longer exposed to the atmosphere and lost, not serving any purpose. Incredibly cool. What also is incredibly cool is that this led our colleagues, our collaborators, Court Strong, over in atmospheric sciences, to identify a new climate teleconnection between the North Atlantic. That's what the figure on the top left is, a cold, warm pattern. And that oscillates roughly every 12 or 13, 10 to 13 years or so, similar to what we saw in groundwater. And that influences our climate in the Western US. And you'll see that the sea surface temperature index, the quad pole, maps very closely with what precipitation here is in the Western US. It hadn't been identified before. What's really cool, don't worry about this slide too much, except to know that it's absolutely amazing finding from Court's group. If you know anything about the climate of the upper Colorado River or the Intermountain West, around 40 degrees north and south, ENSO means nothing for predictability of precip. If you're down south, it means a lot. If you're up where you are in the ENSO cycle. So it's like, oh, it's still a crapshoot. Oh, we're going to have an El Nino year. It's okay, so I'm going to drive south to ski. Oh, we're having an El Nino.
That's right. They were coming for the arts thing. Can I call you back? Can I call you back in a few minutes?
I'm sorry. I need to take this. This is my...
I'm in the middle of a seminar. Well, it's actually getting towards the end.
We can see who it is on the...
So you guys can see who it is. Don't out them.
Stop talking. And then we can see. Denison Bramble. It sounded like Dennis Bramble.
Okay.
Hi, Dennis.
All right. So for someone who is a latent climate scientist, I guess, this interaction, this teleconnection is nothing that I could do. But Another little piece of that Sudoku puzzle gave them a clue to look for what could cause this variability. And that interaction between the North Atlantic and ENSO maps wonderfully in terms of predictability. So I'm trying to get Court to start a business where we use this to predict where to ski each year. Right? He won't do it. Anyway, it's a good idea. Okay, so now we've had major inroads in other fields. We've had inroads in predictability, simple tools that we can use. How do we put it all together? So the figure here on the left is just the relationship between annual precipitation and annual streamflow. Shotgun map, plus or minus 50%. We include base flow, that's the middle figure. Narrow that uncertainty tremendously, and work that Logan Jameson was doing, Bailey's going to be building on a little bit with her work, shows that when you add in the melt dynamics, what's happening during the melt season, you go from 50% year-to-year variability to less than 5% variability in every one of the catchments. It's a simple model. We don't need to parameterize physical models. It's based on the physics in those physical models, but we can then use that to improve prediction. And the way we do that is something that's very, very simple. We're not asking water managers to change what they're doing. This is a partnership that we have with Salt Lake City Department of Public Utilities. We take the information from base flow, we can put it on this table. We take the information from the El Nino North Atlantic and give an idea of what the snow tell, that's what water managers use to predict stream flow, snow tell. And we can take the data in this table is acre feet, annual acre feet of discharge. This is Big Cottonwood Canyon, so brightness in Big Cottonwood Canyon. So in January, every number in that table would be a possibility. With base flow, only the numbers in the row are a possibility. And with base flow and the climate prediction, the improved climate prediction, we can give them a much greater range. And they can do that and start making their plans and provisions in January instead of in April, May, and June, which is what they do now with the current tools that they have. One more part of the sabbatical boondoggle. Kip and I got a little NSF Rapid Award. I wasn't able to travel internationally for a couple of reasons. And so we put in this proposal, we showed some of this preliminary information to NSF, and they gave us money to collect tritium and tritium age dates. And so we can plot runoff efficiency. So the fraction of annual precipitation that falls in a catchment, or that total stream flow for a catchment divided by the total amount of precipitation that falls. So you can't have a value greater than 1. Every now and then we do an analysis and there's a value greater than 1. That's a pretty good check that either we just figured out how to create mass or there's some error in our calculations. But so we look at the runoff efficiency throughout the West is generally pretty low. It's 20 to 40%. There are a couple that are high, up around 60. That's Little Cottonwood Canyon. So the characteristics of the watersheds that control runoff efficiency, the characteristics of the environment, as I showed previously, are related to storage. Storage is the biggest player, and then how the climate forces what happens to the snowpack. That controls that interaction. And the higher runoff efficiency, the younger the water is. That makes sense. But if you talk to almost any catchment hydrologist, especially one involved in prediction, you see that we have a lot of dates between 10 and 20 years old. You would never expect that Big Cottonwood Canyon or Ogden South Fork or any of these snow-covered catchments high in the mountains would have water that's that old in them. The assumption is that there's very, very little storage. So we're still trying to figure this out. Those blue dots are our Wasatch Front sites and the sites in Idaho. Those were the first results that came back. It's like, this is amazing. Look at this straight line. It's never that simple. And of course, it really is never that simple. The orange dots are sites that have a strong monsoon influence. So monsoon's doing something different. It's like, oh, that probably makes sense. So I've been talking now for 46 minutes, and this is the take-home point. we have tremendous issues and challenges in terms of managing our forests, managing our watersheds, and managing water resources. There are a lot of approaches that moving forward to improving this. Some simple metrics that are associated with storage that are grounded in fundamental physics and chemistry of watershed function give us some nice insight. Focusing on this delta S term lets us scale the response. And it opens up new things like these climate teleconnections and the role of humidity. So it's fun to be making progress and to be working with stakeholders. And I'm spending a lot of time working with water managers over the last several years. Like, how can we put this knowledge into your workflow? That's all I have. 48 minutes. Thanks for your attention.